Alright, for number 2 we have a 3 by 3 system of equations. So the first thing I did is I wrote it as a matrix equation, right, where the vector x prime is this 3 by 3 matrix times x. The vector x is, the column vector where the functions are x1, x2, x3. So we need to calculate eigenvalues, which means we have to do a 3 by 3 determinant. It'd be 1 minus lambda, 2, 2, 2, 7 minus lambda, 1, 2, 1, 7 minus lambda. And then to do the 3 by 3 determinant, we'll do the Calc 3 trick, where we take the first two columns and put them on the right side here, and then do diagonals. So we do the first diagonal. That would be 1 minus lambda times 7 minus lambda squared. We do the second diagonal, that'd be 4. And then we do the third diagonal, that'd be another 4. Then we do the opposite diagonals. This one would give us a minus 4, minus 4, 7 minus lambda. Minus 1 times 1 minus lambda. Minus another 4 times 7 minus lambda. Okay, so we're going to have to multiply all that out to see what our characteristic polynomial is. So let's see, we've got 1 minus lambda. If I do 7 minus lambda squared, that would be 49 minus 14 lambda plus lambda squared. 4 plus 4 is 8. I've got minus 8, 7 minus lambda, and then again another minus 1 minus lambda. Alright, so let me multiply all this out here, and I'll try to combine like terms. So 1 times, so I'd have a 49, I'd have a minus 14 lambda, I'd have a plus lambda squared. I'd have a minus 49 lambda plus 14 lambda squared minus lambda cubed. Those are all the terms you get when you multiply, this product here. I have an 8. I'd have a minus 56, a plus 8 lambda. That's when you distribute the 8, and then you'd also have a minus 1 and a plus lambda. Okay, so if you add all that up, what do you get? 49 plus 8 minus 56 minus 1, that all adds up to 0 actually. Okay, and then minus 14 minus 49 plus 8 plus 1, so that would be negative 54 lambda. Then we'd have a plus 15 lambda squared minus lambda cubed. So there's your characteristic polynomial. The eigenvalues are going to be where that's 0. So we have 0 equals this polynomial here, which, notice what you could do, you could factor out a negative lambda, right? And then you'd have a lambda squared minus 15 lambda plus 54, which, now you realize the quadratic would factor as lambda minus 6 times lambda minus 9. And so we get lucky because you can factor the cubic. You get 3 real distinct eigenvalues, 0, 6, and 9. Okay. Now we have to find the eigenvectors which go with those eigenvalues. Okay, so let's see, lambda equals 0. Let's see. What we have to do, remember, we have to go back to this original matrix here, plug in lambda equals 0, and find an eigenvector. So we'd have 1, 2, 2, 2, 7, 1, 2, 1, 7, and we're trying to come up with a non-zero eigenvector which makes all of those equal to 0. Okay, and the easiest way to do this is to take out your calculator and RREF that system. So we want to, first of all, we want to edit a matrix. It's going to be a 3 by 4 matrix. We're going to have 1, 2, 2, 0. That's the first equation. 2, 7, 1, 0. 2, 1, 7, 0. That's the third equation. We'd want to RREF that system to figure out what the solution is. Okay, and notice what you get here is, you get the third equation is just a bunch of zeros, and so really what this means is that V1 minus V3 is 0, so that just means that V2 equals V3. Right, I'll write all this down. So actually, yeah, here's what the calculator looks like when we RREF it. And really, yeah, that corresponds to a system where V1 plus V3 equals 0, and V2 minus V3 also equals 0. Okay, whoops, but it should be a 4 V3 here. Okay, so yeah, there's going to be lots of solutions. The easiest one would be, V2 has to be equal to V3, so choose them both to be 1. Okay, that would satisfy the second equation. And then, in order for the first equation to be true, V1 would have to be negative 4. Okay, so the eigenvector we choose here would be negative 4, 1, 1. We do the same thing with the other two eigenvalues, right? The next eigenvalue is 6. Okay, so we take this matrix, but remember it's the diagonal entries are actually minus lambda. So 1 minus 6 would be negative 5. So we'd have negative 5, 2, 2, 2, 1, 1, and then 2, 1, and then 7 minus 6 is 1. Okay, we're trying to find an eigenvector that works for that eigenvalue, and we can just go back to the matrix, edit the matrix. Notice it's just going to be the diagonal entries that change, right? The first diagonal, the first entry changes to negative 5. The second diagonal changes to 1. The third diagonal also changes to 1. Now if we RREF, we get this system. Which says that V1 equals 0 and V2 plus V3 equals 0. And so the easiest way to do so, V1's got to be 0. But as long as V2 is the opposite of V3, we're okay. So choose one of them to be 1, the other one to be negative 1. Okay, so the eigenvector that goes with 6 will be this one. And then finally, we got lambda equals 9 here. So all we're doing is just taking the original matrix, but having lambda equals 9. So let's see, what would that give us? On the diagonal, that would give us negative 8, negative 2, and negative 2. Okay. So actually, let's not even bother writing it all out. Let's just edit our matrix. And yeah, the diagonal entries are now -8, -2, and -2. And now I RREF that matrix, and I get this. Which tells me that V1 minus half of V3 equals 0, and V2 minus V3 equals 0. So what should I choose for my eigenvector here? Well, let's choose V2 and V3 to both be 2, and that way V1 would end up being 1. Okay, that this triple here satisfies the system, so that's a good eigenvector. So what's the general solution? It's going to be e to the 0t times the first eigenvector, which was -4, 1, 1, oh, C1 in front of that one, and then C2 e to the 6t times the second eigenvector plus the C3 e to the 9t times the third eigenvector. That's going to be the solution.